In this video tutorial, we are going to explore one of the most powerful yet easy to understand algorithm in machine learning, decision trees. By the end of this video, you will understand how decision trees work, their strengths and limitations, and how to implement them in Python. So what is a decision tree? A decision tree is a supervised machine learning algorithm used for both classification and regression tasks. It splits data into smaller groups based on feature values until it reaches the most accurate classification. As you can see in this figure, a decision tree starts with a root node which represents the entire training dataset. It then splits into branches based on decision rules, forming the internal nodes. Right, the process continues until we reach the leaf nodes. So these leaf nodes represent the final classification outcomes. Right, the goal here is to create pure nodes where most data points belong to the same class. Right, so how do the decision tree work? So we are going to look at an example here. Say, for example, we have a satellite image and we have training sample points that represents forest and non-forest. And we have three features. Specifically, we have three spectral bands that we want to use for the classification. So we have the green band, red band, and near-infrared band. Right, so as you can see, the decision tree start with the root node here. So this is the first decision point. Okay, so what are the initial conditions? So first, the decision tree algorithm is going to select the green band as the main feature for doing the classification. Right. Here, the green band should have a spectral reflectance of less than or equal to 0.503. And the Gini index, which indicates the level of impurity here, indicates that there is a 50% chance of misclassification. And here we have the total number of sample points is 280. And for the values, we have 137 sample points representing non-forest and 143 sample points representing the forest areas. So the dominant class in this first node here is the forest, because we have more forest areas than the non-forest areas. Right, so let's look at how this works. So okay, so we the tree first splits the data based on the green band, actually the green spectral band. So if the green spectral value is less than or equal to 0.503, it further checks the near infrared value. So this condition is true. Right, so if here the near infrared is less than or equal to 0.776, the area is classified as a non-forest. Okay, so if you see here the Gini index here is 0.91, which is quite low. So here the algorithm is confident that this is a non-forest. And again, if you see the total sample values, we have 131 and 117 represent non-forest. And as it goes down, as it further splits, it gets a much lower Gini value of 0.037, which means here we almost have a pure non-forest class. Okay, so otherwise, if it goes the other direction, we have a Gini index of 0.5 again, which is 50% of misclassification. So here, but we have about 24 sample points with the 50% misclassification, but it's given as non-forest, but this is not a very pure point. And then if the green value is greater than 0.503, it checks the near infrared. Here the condition is false. So if the near infrared is less than or equal to 0.745, the area is classified as a forest. Otherwise, it's going to perform another check, and then here we have a non-forest class. But if we look at the Gini index here, we have 0.182, which is very low. So it means we will have more chances of having the forest class. Right. So this is how the decision tree works. So the decision tree here that we've used uses the Gini index to measure the impurity of the splits. So this aims to create the pure nodes where one class dominates, as is in this case, where we have the one class dominating, in this case forest, in this case non-forest. Okay, so there are different types of decision trees. So decision trees algorithms. So the most common algorithm here is the classification and regression trees, which is called CAT. So this is the one which is commonly used. It splits the data using the binary splits and as a cost function. And then we have the ID3, the iterative dichotomizer 3. This is suitable for categorical features. It does not handle continuous data directly. And then we have the C4.5. So this is a successor to ID3. It handles continuous features, and we can also perform pruning here. And then we have the C5.0, which is the improved version of the C4.5. So this is faster and more accurate than the previous versions, and it handles the missing data values better. Right, so in this tutorial, we'll be focusing mostly on the CAT algorithm, which is widely used with scikit-learn in Python. Right, so how does a decision tree decide where to split? So a tree splits the data set based on the criteria or the measure of impurity. So usually we have two measures of impurity that we use with CAT. So one is the Gini index, and the other one is the entropy. Okay, so the Gini impurity measure is used in the CAT algorithm, measures how often a randomly chosen sample would be misclassified. Okay, so a lower Gini means more purity. Okay, that means a better classification or a complete class. Right, the Gini impurity measure is faster to compute. So this is the formula for calculating Gini. And as you can see here, we have the decision boundary showing how this Gini impurity splits the training samples. In our case, we were interested in the forest and non-forest training samples. And next we have the entropy. So entropy measures the level of disorder in a training data set. Okay, so it is slightly slower than the Gini impurity index. This is because it considers logarithm calculations. So this is the entropy formula. This is how we calculate entropy, and this is the decision boundary, showing how it splits the data. As you can see, it's a bit different from the one using the Gini index. But in some cases, entropy is actually better in classification. So anyway, you need to compare the two if you plan to use the decision tree, especially with CAT. Right. So the key difference is that the Gini is faster than entropy. However, as I stated, in some cases the entropy is more precise, especially for classification. Right. So next we want to implement a decision tree in Python. So as usual, we are going to build a decision tree here using the same data sets that we have used in the previous video tutorials. So here we are going just to create a synthetic data set that consists of 400 training samples. The training samples have got 3 features, that is the green, red, and near infrared. Okay, so these are the independent variables, or the predictors as such. And here the target classes, okay, the one that we want to classify is the forest and non-forest. So we only have 2 classes. Right. So if we run this code, we are going to have the representation of the forest and non-forest in 2D space. So just displaying using the near infrared and green band. Right. Next is just a function that we've used, that we've defined previously as well. So this function just is for plotting the decision boundary, because we want to see how the 2 different splitting algorithm, the Gini and entropy, classify the forest and non-forest areas. Right. So first we start with the decision tree, focusing on comparing the Gini and entropy. So here we are just going to first import our decision tree class, which we are going to use for classification. So this is available in the scikit-learn machine learning algorithm. So we are going to get the scikit-learn tree, and then we want to do the classification. So we are importing the decision tree classifier, and then we also want to plot it, to plot the decision trees boundary, as well as the actual decision trees, the actual trees. Right. So here we have 2 decision trees with different criteria. So the first is using the Gini impurity index. Then the other one is the entropy. And for the other hyperparameters, we are just keeping maximum depth of the tree to 3. Okay, we are just keeping maximum depth of 3. And then we do our usual fitting the model. So remember, from our training samples, we split the training sample into training and the test data set. Right. So if we run this code, we are going to be able to display the decision boundaries. So here we have our decision boundary based on the Gini, and as you can see, this is the split. The red dots showing us our forest area, and the blue showing the non-forest. In some cases, we have instances of the non-forest in the forest area. And this is the same case also for entropy. Also, although the split is a bit different from entropy. So look at the decision boundary that we have here, showing the forest and non-forest. So here it attempts to do a better classification, but however, still we have some instances of the non-forest classes. Right? If we look at the accuracy levels, we have 85% for the Gini and 83% for entropy. So when you run with the real-world data set, please also try to check by running these two different splitting algorithms. Right. So finally, we want now to plot the decision trees, the actual decision trees, based on this two splitting algorithm, the Gini and entropy. So this code is just showing us how we do the plotting, the figure for the decision tree for the Gini and for entropy. So here is our result. Okay, so let me just reduce it so that you can see. Okay, so this is our first decision tree based on the Gini impurity measure. And as you can see, again, we have our initial conditions. We have the green band as the starting point. And if we look at the final classes, here at the bottom, in the extreme left here, we have a pure class here, representing non-forest. So the Gini index here is 0.0. And we have a value of 95. So this is this is a pure class of forest. So this is what we would want in the real world. And next we also have the next level of impurity. And here we also have a classification of non-forest. And so is the third. And then if we look for the forest classification, the lowest index that we have here, lowest index indicating the pure forest is 0.108. Here, please note that we have 115 points that have been classified as a forest. So this is a pure forest class. And also here we also have less another index showing the forest, another lower Gini index showing the forest class. Right. Next we look at entropy. And if we look at entropy, we look at the splits again in the extreme left here. We have an entropy of 0.0. So again, this is indicating a pure class of non-forest. And interestingly, we also have a pure class of forest here. So we have an entropy of 0.0. And the samples value of 71 and 71 classes are non-forest. So this is just the difference between the two splitting algorithm. Right. So it's important that when you run the decision tree for your data sets, it's better you test between the different splitting algorithm as well as the different hyperparameters. For example, change the depth of the trees so that you can try to improve your classification. Right, so what are the strengths and limitations of decision trees? So number one is that they are simple and interpretable. So as you can see, you can visualize and you can explain how the algorithm is doing their classification. Second, it does not need any feature scaling and it works very well with both numerical and categorical data. Next, it also handles nonlinear data. So this is good because it can capture complex relationship between the features, and it can also be used for feature selection. That is, we can identify the important variables that have more significance in the classification. So what are the limitations? Decision trees are affected by overfitting. Okay, this is because they tend to memorize data if the trees are not pruned, and they are very unstable because the small changes in the data set can lead to very different trees, so it becomes very difficult to get a very good classification or regression result. And it is also affected sometimes by bias splits. For example, if you've got a data set which is highly unbalanced, for example, we have more of non-forest than the forest, then the non-forest are going to dominate the class splits. So this is not good. And then finally, it is not optimal for large data sets because it can be computationally expensive to construct the decision trees. Right, so this is all about the decision trees. I hope this video tutorial was useful. And next we will be looking at an improvement of decision tree. We'll be looking at the random forest. So see you in the next video.